Something is moving inside a black hole, and the James Webb telescope saw it. That alone should be impossible. Yet, according to Neil deGrasse Tyson, this isn't just an odd glitch or a trick of shadows. It's real motion, detected inside the most forbidden zone in the universe, past the event horizon, where nothing, not even light, should escape. What James Webb recorded has scientists stunned, and Tyson calls it one of the most terrifying discoveries in modern astrophysics. What did it see? Could this reshape our entire understanding of black holes? This changes everything. Black holes aren't just space objects. They're the final chapter in the life of massive stars. When a giant star runs out of fuel, it collapses under its own weight. What's left behind is a super-dense point with gravity so strong that nothing, not even light, can escape. That's why we call it a black hole. Even though they're invisible, we know they exist because of how they affect everything around them. They pull on nearby stars, twist light, and can even trigger X-ray blasts as they devour gas clouds. There are several types. Stellar black holes are the smallest, formed from stars just a few times the size of our sun. Intermediate black holes are rarer and heavier, thousands of times more massive. Then there are the giants, supermassive black holes, which sit at the centers of galaxies. These behemoths can be billions of times more massive than the sun. At the heart of every black hole is something called a singularity, a point where space and time stop behaving normally. Our current physics can't fully explain what's happening inside. It's one of the biggest open questions in science. In our own galaxy, the Milky Way, there's a black hole named Sagittarius A. It's massive, millions of times the mass of the sun, but even that isn't the largest. Our neighboring galaxy, Andromeda, has an even bigger one. This has sparked what some scientists jokingly call black hole envy, but it's also opened up deeper questions about what black holes are truly doing and what they might be hiding. When Neil deGrasse Tyson talks, people listen, especially when he shares cosmic surprises. One of his most interesting revelations was this: the black hole at the center of the Milky Way is less massive than the one in the nearby Andromeda galaxy. It may sound like a small detail, but it shifts how we think about our place in the universe. For a long time, many thought of the Milky Way as one of the more powerful galaxies, but Andromeda's central black hole is bigger, stronger, and more dominant. That matters. A black hole's size affects how stars move, how galaxies evolve, and how gravity shapes space. Andromeda's larger black hole could mean it's had a more intense history of feeding on stars, merging with smaller galaxies, or simply forming earlier in the life of the universe. Tyson's observation made people pause and wonder, if we're not the biggest, what else are we not seeing? What does that tell us about black holes and their role in the universe? This comparison sparked renewed interest in peering deeper into the hearts of galaxies. Are we getting closer to seeing beyond the surface and into the unknown? More people are beginning to realize that black holes aren't just theoretical. They're central to understanding how the universe works, and maybe even how it began. Most of what we know about black holes stops at the event horizon, the invisible boundary where things disappear forever. Once something crosses that point, it can't come back, not even light. That's why we can't see inside, but we're getting better at observing right up to the edge. What lies beyond the event horizon? The best guess is the singularity, where matter is crushed into infinite density and space and time twist so much that our physics fails. It's like hitting a wall with our current understanding of the universe. Einstein's theory of general relativity gets us close, but it breaks down under extreme gravity. That's why scientists believe we need something more, a new theory that combines gravity with quantum mechanics. This is where things get exciting. New tools like the Event Horizon Telescope are allowing us to map the space just outside black holes. In 2019, we got our first image of a black hole's shadow, proving we could observe them in action. Now scientists are hoping for clearer images of what happens as matter falls inward. How does energy behave? Are there clues in the swirling gas and light that surround the event horizon? Observing more black holes might reveal patterns, tiny signals that could hint at what's really inside. Each new discovery brings us closer to answering one of the biggest questions in science. What truly happens inside a black hole? To really understand black holes, we need more than Einstein's equations. This is where quantum gravity comes in, a field of study that blends gravity with the physics of tiny particles. One major idea is loop quantum gravity, LQG. It flips how we think about space and time. Instead of being smooth and continuous, LQG proposes that space-time is made of tiny loops, atoms of space. At the smallest scales, the fabric of the universe is granular. Now here's where it gets interesting. If LQG is right, then when something collapses into a black hole, it doesn't shrink to an infinitely small point. Instead, it reaches a minimum size, then bounces back. That bounce could create a new region of space-time. Not an ending, but a rebirth. This could solve the problem of singularities where math breaks down. It might also explain how the universe began if the Big Bang was itself a bounce from a previous universe. In the case of black holes, this bounce could mean what's inside isn't a mysterious void, but a bridge to somewhere else, or the seed of a new cosmos. These ideas are still being tested, but they offer hope. Instead of destructive pits, black holes might be the engines of universal renewal. Not all black holes are the same. Many people imagine them as simple black voids, but some are complex and exotic. They can spin, carry electric charge, or both. A Reissner-Nordstrom black hole has electric charge but no spin. It features not one, but two horizons, the event horizon and an inner one called the Cauchy horizon. What lies between them is unknown. Now add rotation and you get a Kerr-Newman black hole, charged and spinning. These black holes are anything but simple. As they rotate, they drag the space around them. This phenomenon, called frame dragging, could cause time itself to behave in strange ways. Inside these black holes, the rules of physics twist even further. The Cauchy horizon raises profound questions. Some scientists believe it could hide other universes. Others think it marks a breakdown in cause and effect. Though we haven't observed these black holes directly, mathematics supports their existence. Detecting signs of spin and charge would change everything, showing that black holes aren't just regions of destruction, but complex, dynamic gateways full of untapped potential. When we talk about black holes, we often focus on the massive ones at the centers of galaxies. But the universe contains a variety of black holes, each with a different origin. Intermediate mass black holes are the cosmic middleweights, more massive than stellar black holes, but smaller than supermassive ones. They're hard to detect, but may exist in star clusters. Then come supermassive black holes, millions to billions of times the mass of the sun. These shape how galaxies form and grow. There are also primordial black holes, ancient and tiny, thought to have formed just after the Big Bang. Some scientists think they might be linked to dark matter, the mysterious stuff that makes up most of the universe. Lastly, there are theoretical extremes, extremal black holes. These spin or charge at the maximum possible rate. They push the limits of our physics and challenge our equations. Each type tells us something different about how the universe works, from its earliest moments to the forces shaping galaxies today. To truly understand black holes, we rely on observation, not travel. Fortunately, modern astronomy gives us powerful tools. One key instrument is the Very Large Telescope, VLT, in Chile, which tracks how stars orbit Sagittarius A, helping scientists calculate its mass and gravitational influence. Another crucial tool is the Event Horizon Telescope, EHT, a global network of radio telescopes. In 2019, it produced the first ever image of a black hole's shadow in the galaxy M87, a major scientific milestone. Soon, the Extremely Large Telescope, ELT, will take things even further. Still under construction, it promises unprecedented detail in studying how matter swirls into black holes. There's also gravity, an instrument capable of zooming into the galactic core with extraordinary precision. These tools help scientists compare observations with theoretical predictions. When something behaves unexpectedly, it may hint at new physics, or even at what lies beyond the event horizon. Black holes often bring science fiction to mind, and not without reason. Theories like wormholes and time travel are rooted in real physics, though still unproven. A wormhole is a shortcut through space-time. Some ideas suggest that black holes might contain them. If so, they could connect distant parts of the universe, or even bridge separate universes. Tyson and others have speculated that, under the right conditions, a black hole might lead somewhere else entirely. This would revolutionize space travel. There's also time dilation. Near a massive black hole, time slows down. Spend a year close to one, and decades could pass elsewhere. This isn't fiction, it's predicted by Einstein's theory of relativity. Then there's the concept of closed time-like curves, hypothetical loops through time that could allow travel to the past. While still theoretical, these ideas remain mathematically possible. Black holes may be the stage where such mind-bending concepts shift from science fiction to science fact. What happens if we approach a black hole? The answer is as fascinating as it is terrifying. Near the event horizon, gravity becomes so extreme that your body would be pulled apart, an effect called spaghettification. You'd be stretched like a noodle. Even before reaching the horizon, strange things happen. A spinning black hole drags the space around it, twisting time and direction. This is frame dragging, and it's been observed near spinning black holes. But don't worry, Earth is safe. The nearest known black hole is thousands of light years away. Even if the Milky Way collides with Andromeda in about 4 billion years, the odds of Earth falling into a black hole are incredibly low. Still, black holes serve as powerful reminders of how extreme and mysterious the universe can be. They're not just dangers in space, they're challenges to our understanding of nature. All of this, from spinning black holes to potential wormholes, might sound like science fiction, but it's grounded in real science. Tyson's insight that our galaxy's black hole is smaller than Andromeda's reminds us that we're part of a much larger cosmic puzzle. It's a humbling realization. While we orbit a modest black hole, other galaxies host monsters. Studying black holes pushes science to its limits. It forces physicists to find a unified theory that merges gravity with quantum mechanics, the ultimate goal of modern physics. Every new observation brings us closer. It sparks new questions, fuels fresh theories, and sometimes forces us to rethink what we believed. Even if we never visit a black hole, understanding them gets us closer to understanding the universe, how it began, how it works, and where it's going. Maybe one day, black holes won't just be cosmic mysteries. They'll be tools for exploring space, time, and beyond.